In the last couple of videos, I have already introduced you to the idea of work. Here's the idea. If you have a mass which goes through a displacement d while acted on by a force, then the work that the force does on the mass is equal to the magnitude of the force times the magnitude of the displacement vector times the cosine of the angle between the two vectors. In this video, I'm going to tell you why work is a useful concept. Work is a useful concept because the work done on an object can be connected to the motion of the object using something called the work-kinetic energy theorem. Before I can introduce you to the work-kinetic energy theorem, first I have to introduce you to the idea of the kinetic energy. The kinetic energy is one way of quantifying the motion of an object. If we have an object with a mass m moving at speed v, we then define the kinetic energy of the object as 1/2 the mass of the object multiplied by the square of the object's speed. I'm going to do a simple example to compute the kinetic energy of a moving object. And from there, we will go into the work-kinetic energy theorem. So here's just a quick calculation to illustrate. Let's say that we have a 3-kilogram object, and it is moving at 10 meters per second. We would like to find the kinetic energy of the object. So this is just a straight substitution into the formula. We have kinetic energy equals 1/2 the mass times the speed squared. So now substituting, we put in the mass, 3 kilograms. We put in the speed, 10 meters per second. That gets squared. Okay, so the numerical value would be 3 times 100, 300 divided by 2, which would be 150. Now let's look at the units. Here we have kilograms. Now this got squared, so we have meters squared over seconds squared. Now, do you recognize this combination of kilograms, meters, and seconds? It is a joule. So we can say that the kinetic energy of this mass is 150 joules. And now we have calculated a kinetic energy for a particular moving object. Let's look at the work-kinetic energy theorem now. To start, let's say that we have an object with mass m, and that object is going to go through a displacement. So let's say that the object starts here, ends up here. We have a displacement vector which goes from the initial position to the final position. Let's say that as the object goes through that displacement, it has several forces acting on it. Maybe that includes a force F1. Maybe that includes a force F2. Maybe a force F3. And of course, I can keep going like this. Let's also say that when the object starts over here, it has a speed v initial. And when the object gets over to here, it has a speed v final. The work-kinetic energy theorem says that the change in the object's kinetic energy is equal to the sum over all work done on the object by all forces acting on it. Again, the change in the kinetic energy is equal to the total work done on the object by all forces acting on it. This is such an important statement that I'm going to actually write it out in words. So on the left side of the equation, we have the change in the object's kinetic energy. That is equal to the total work done by all forces acting on the object. There are a variety of different ways we could write out the work-kinetic energy theorem. My favorite, at least my favorite as far as applying it to solving actual problems, is to write out the change in the kinetic energy explicitly. The change in anything is the final value minus the initial value. Since the kinetic energy is defined as 1/2 the mass times the speed squared, then the final value would be 1/2 mass times final speed squared. Then we subtract the initial value, 1/2 the mass times the initial speed squared. And then that is equal to the total work done on the object by all forces acting. So this is our work kinetic energy theorem. And in the next couple of videos, we're going to be doing example problems using the work kinetic energy theorem.